presentation on his dissertation work, and feel free to ask questions while he's given it, and there'll be some opportunity for questions when he's finished as well. So go ahead, Stephen.
Cool. Well, thank you all for coming and hanging out while I talk to you a little bit about my research on limited information strategies for topological games. So we're going to talk about topological games. Let me define what that is for you. Topological games are two-player games, and they're actually infinitely long. There's one round for every non-negative integer, and they're defined for topological spaces. During each round, what's going to happen is you're going to have player one and player two. They're going to take turns, and depending on the game, what they choose will be different. There's always going to be something topological, a point of the space, an open set in the space, or perhaps an open cover of the space. We'll see some different examples. At the end of the game, so it took infinitely many rounds, but at the end of this game, you're going to have two infinite sequences of those choices that were made by either player. And by inspecting those sequences of choices, a winning condition is defined for the game based on those choices, and that'll declare the winner. The study of these games involves finding when a player has a winning strategy. And a winning strategy is basically a function. It takes in finitely many moves of the opponent, and it determines what that player's next move should be. If you think this stuff is cool, at least as much as I do, there's an excellent survey paper by Telgarsky that I've referenced at the end of the presentation. So, I'm going to talk about the granddaddy of them all, the Banach-Mazur game. Some people call it the Showcase game. It's pretty straightforward. So I'm going to describe what happens in the first 3 rounds. In round 0, player E goes first, and she'll pick an open set. Now, if you're not a topologist, then what you should just do is think of X as being something like the real line or the real plane or the rationals on the real line, something like that. And these open sets are just little balls, something with some substance to them and no boundary. So E picks this open set, N picks an open subset, E picks an open subset, so on and so forth. And they're going to, of course, get smaller and smaller, but the question is how small? The first player, player E, is trying to make it so that the intersection of these guys is actually empty. There's nothing that could possibly be in every single one of these circles by the end of the game. Player N will win otherwise. We don't have any ties in the topological game. All right, so let me just, for example, if you were thinking about X as the XY plane of real numbers, then N's happy, because N can make sure that the open set she picked have closures inside the last one, and she can make sure that they are compact as well. The intersection of compact sets is not empty, so she can make sure that these purple sets have non-empty intersection. No problem. However, what if your X is the rational numbers? Anything countable in T1, in fact, is good for player E, because player E can say, okay, I'm going to take the first rational and forbid it from being in the intersection during the 0th round. The second rational I'll make sure is not forbidden in the first round, so on and so forth, taking care of all these countless many things by the end of the game. They cannot be in the intersection if at some finite point they were forbidden from being in the intersection. So that'll do it. So what's the point of these things other than just the fun of mathematics? Well, a topological space is bare if and only if it's the countable intersection of open dense sets is itself a dense set. But there's also this game theoretic characterization. If E does not have a winning strategy in the Banach-Mazur game, which I denote with this up arrow means there is a winning strategy, so crossing it out means that there does not exist one. That also turns out to characterize the bare property. And thus the topological property of being bare has a game theoretic characterization. What I'm interested in, though, is that what if these strategies that we're talking about, you have to keep up with a lot of stuff. It's an infinitely long game, and at some point you're going to be dealing with millions and trillions of previous moves. What if your information that you're allowed to use, what if your memory is finite? Well, that would be called a limited information strategy, and that might characterize a stronger property of the space. So consider the following. There are 3 topological properties here. I'm not going to define all of them. Alpha favorable, Showcase, and bare. If you're alpha favorable, you're definitely Showcase. If you're Showcase, you're definitely bare. And the way I know that is because I know the game theoretic characterizations of each of these guys. Alpha favorability is characterized in having not just a winning strategy, but this tact here means she has a winning tactical strategy. A tactical strategy doesn't care about the entire history of the game. All it does is say, well, what's the most recent thing that you played? Okay, I'm going to do this because of that. and then I'm going to forget it forever. And then, okay, well, now what'd you do? All right, I'm going to do that. It's only going to consider the most recent move of the opponent at any time in the game. Now, if you can play a game only remembering some of the stuff and win, then you can definitely win the game remembering everything, the entire history. So if you're alpha favorable, you're definitely show K, because show K is characterized by having any old winning strategy. However, if the topological space X doesn't have enough structure, it could be show K, but yet not be alpha favorable, because you're going to have to exploit some of the structure of X in order to ignore the history of the game, in order to make that irrelevant. All right, so this is kind of my motivation for studying this stuff. By characterizing topological properties using the theory of topological games, basically it gives us some new proof techniques. For you give me a space, I can prove that it's bare by taking an arbitrary collection of open dense sets and proving that the intersection is empty. Or I can prove to you that any strategy for player E is not a winning strategy for the game, using the game theoretic characterization. The aim of my dissertation was to investigate 4 topological games from the literature and try and find some new limited information implications of those. So, in doing so, I found some new results in general topology, and this research connects with research of that of my advisor, Gary Grunhaig, not to mention Peter Nikos, Dr. Telgarsky, Dr. Bell, and Dr. Skippers, and others. You'll see littered throughout the talk. All right, game number 1. This game is due to Dr. Grunhaig, and there's 2 variations. There's a convergence game and a clustering game, and I'll tell you how this goes. During each round, player O goes first. Player O will pick an open set containing a particular point designated at the start of the game. Player P will respond by picking a point inside of that open set. Now in the next round, player O will pick a new open set. It doesn't matter which one, as long as it contains that point. Player P then has to play within the overlap, the intersection of those 2 open sets. Play round 2, player P always has to play within the intersection where all of the previous open sets overlap. The goal of this game is for O to win if the points chosen by P converge or cluster, depending on which version we're talking about, to the particular point X within the space. Convergence means that for any open ball around that point, it contains all but finitely many. Clustering means it contains infinitely many, even if it misses infinitely. Even if it misses infinitely many, that's okay. For clustering, as long as it contains infinitely many. Notice that O doesn't have to really pay attention to what she did in previous rounds in order to make legal moves. O in general won't remember what happened in all the previous rounds. Okay, so why do we care? Well, let's say that O has a winning strategy for this game at a particular point X in the space big X. We're going to call that thing a W point. Now, all points of first countability, all points that have a countable base of open sets at that point are W points. You can just pick the next one in that countable base. But there are spaces, the one-point compactification of an uncountable discrete cardinal, for instance, the infinity point does not have a countable base, but you can still win this game. Because what the open set picker can do is basically say, I forbid, you play this, you can play that ordinal now, that's fine, but I'm going to make sure I never allow you to play that ordinal again for the rest of the game, because she has perfect memory. So by doing so, the points chosen by the opponent have to all be different or be infinity, and that's going to cause convergence to infinity. Now, a thought that I had, just a silly thought, was, well, actually, can't we just take the first countability, this open base, this countable base of open sets, and characterize that using this game? And it turns out, yeah, you can, by using what's called a winning predetermined strategy, which basically means I'm not going to pay attention to what you're doing at all. I'm just going to keep track of what time it is. What round is it? Round 10, I played this open set. Round 20, I played that open set. Ignoring the points that are actually played. And it turns out if you have a countable local base, that's what you can do. You're just going to pick from that countable open base. But it turns out if you can do this, you must have had a countable open base in the first place, if and only if. Another useful idea is this idea of a W space, which we'll talk about later. That means every point is a W point. Every point has this winning strategy for this game for player O. Okay, so what did I do? Now, my results are actually about an alternate version of the game, a variation. I call it the hard convergence game and the hard clustering game, because notice that now player P only has to respect the most recent open set played by player O. This is not a problem if player O has perfect information, right? Player O can always just pick things that are smaller and smaller, and then it doesn't matter. But with limited limited information, there's going to be some difference, because player O cannot remember what happened in previous rounds because she can only see so many of the moves of her opponent, and she can't remember any of her own, so she can't reconstruct them. Okay, so what did I do? Well, first of all, a result by Peter Nikos. Nikos said, hey, there's not going to be a Markov winning strategy for this one-point compactification of the first uncountable cardinal. And that Markov strategy, what does that mean? That means it only considers the round number and the most recent move. Okay? But you can do better than that. It turns out there's actually not going to be a K Markov strategy. So you could keep up with, say, I'm only going to have memory for 1,000,000 moves of my opponent. That's not good enough. This game's infinitely long. Eventually you're going to start forgetting stuff. And when you start forgetting stuff, the opponent to player O can exploit that and beat you at this game. Okay? Interestingly, the strategy which prevents that convergence doesn't prevent clustering. So you can prevent all but finitely many from being in that open set, but you can't prevent infinitely many being in those open sets. Unless the cardinality space is sufficiently large. So for the first uncountable cardinal, there is a Markov clustering strategy, but for the second, the next bigger cardinality, the next bigger size, there's not going to be any Markov strategies, no matter how many moves you keep track of. But knowledge of the round number is definitely used. So if you drop off the round number, Markov means the last move in the round number, but if you suddenly forget the round number, all you remember is the last move. If all you remember is the last 1,000,000 moves, that's no good. You're not going to be able to win the clustering game. So I'm going to talk about these two results right here. I'm actually doing a quick proof of both of those for you. So first of all, I'm going to prove that for the first uncountable cardinal, for one-point compactification of that, there is a Markov clustering strategy. So here's what we're going to do. For every ordinal smaller than the first uncountable ordinal, well, if it's the first, this is the first uncountable one, so all these have to be countable. That means we can get this injective function from that set into the non-negative integers. Now, if you have any finite collection of these guys, there's going to eventually be some non-negative integer, which these functions map everything below it, essentially. That's what we're going to use. If we have a Markov, we're going to define a Markov strategy, and here's how we're going to do it. I see at any point in this game, my opponent has picked a point of the space, it's a countable ordinal, and I know what round it is. That's all I know. But here's what I can do. I can take this point, I can take the next bigger function from this collection, f alpha plus 1, and I can forbid everything that maps to less than the round number by that function. It's going to be finitely many of those, so that's okay. I forbid all those from being in my open set, so my open set's everything else except for those. And that's going to get me a winning strategy. It's going to cause clustering, because the only way you can prevent clustering from happening as the point picker is if you stay within the same finite number of things. All right? However, for any finite collection of things, there's eventually a round where I'm going to take care of all. So by taking care of all those, I've prevented you from staying in finitely much stuff. Eventually you're going to have to get bigger. You're going to have to always get bigger eventually. Or you're going to have to play at infinity itself infinitely often. And now, in any case, you're going to get some clustering or convergence going. So that gives you the winning strategy. I definitely use, though, the round number right here. That was important. What if I don't have that round number? Okay. So now, what if I want to prove there's not a tactic? The way I usually do it is, let's just say you have there's a tactic. Let's prove that it can't possibly win the game for every counterattack. So we take this tactic. This set can be closed and unbounded. I'm just going to do a one tactic, but I will note that this proof works for any K tactic. If you remember 1,000,000 moves, it won't help you either. All right. But we have this thing that only considers one move of my opponent, and I'm going to construct this set, and it's going to be closed, and more importantly, it's going to be unbounded in the uncountable ordinal. I'm going to take every countable ordinal, such that if you're below it, then you're going to be forbidden by the strategy. Excuse me. Everything forbidden by the strategy that's below it is going to be less than alpha. That's what I meant to say. That turns out to be unbounded due to a theorem from set theory. If you have an order isomorphism, because you have this closed and unbounded set of omega 1, that's going to be order isomorphic to omega 1 itself. You have this order isomorphism. I'm going to pick an n less than omega such that this thing right here can forbid at most finitely many things. there's infinitely many things less than the first infinite ordinal. So I'm going to pick one of the things that we didn't forbid, call that n. That's going to be in that set. All right. So now, notice that because it's an order isomorphism, the omega gets mapped above the n. And so that means that the sigma of omega is going to be okay. The things forbidden by n have to stay below it. So that follows then that I can just repeat this n and this omega where they get mapped to, and that's going to be a legal counterattack. I chose this n so it's always in the sigma, and vice versa, this omega thing is always in the other sigma. And that's going to cause me to go back and forth between the same two things. There's no way I can converge way out here to omega. And so that's going to be a winning counterattack that defeats the tactic, because my opponent did not use the round. That's game one. Game number two is actually a really recent development. It was first published about, actually by myself and Dr. Grunhage, but it's due to another mathematician, Jocelyn Bell, who also published about it for the first time in 2014. It's related to the game I just described, and I'll say why in a moment, but here's the idea behind it. Let's assume that our spaces are compact and zero-dimensional just because it gives us a much nicer explanation of how to play. In this case, player D, I call it an entourage picker, but I really, in this case, can call him a partition picker, because they will partition the space, essentially. All right? The point picker then can pick any point that she wants in the space during this initial round. And player D will pick another partition. Player P will pick another point, but notice what I've shaded here. The blue area corresponds to the part of the partition that she played in previously. So she's not just picking a point, she's also picking the area that she's going to play in for the rest of the game. So this portion is blue, and she has to stay inside of it for the rest of the game. So she picks this point. All right, D picks another partition. We combine all those partitions together here. Notice that this is the part that the most latest point was played in. So P has to stay inside of it for the rest of the game. She picks a new point, so on and so forth. Now, D's going to win this game if the points converge, not cluster. They have to converge, but they can converge to any point whatsoever. If that's not going to happen, player P is going to win. Okay. So we say that a space is proximal compact if the player D has a winning strategy for this game, this partition picker. Really, this just defines proximal, but I'm assuming all spaces are compact for this talk, for this game. This game was brought to my attention because it has a very strong relationship to the game I just described to you. Every proximal space turns out to be a W space. That means that if you have a winning strategy for this Bell's proximal game, you have a winning strategy in Dr. Grunhage's convergence game for every point in the space. And the idea, since I have a chalkboard, I guess I'll just draw it real quick. Topological space X, you got some point inside of it. The idea is that you take any point that's in the space, and then you can always move into that X. Then you pick any other point, and then always move back to that X, vice versa, back and forth, always playing X every other round as the point picker in the proximal game. Well, if that causes convergence, since you played X every other round, it's going to cause convergence to that particular point X. And that's the idea of how you take a winning strategy here to force convergence, not just anywhere, but to that special point. Okay. Proximal spaces are cool. They have very strong preservation properties. If you are a closed subspace of a proximal space, you are also proximal. The idea is you take this winning strategy for the big space, just look at the smaller space and use it there. No problem. If you're a sigma product of proximal spaces, which is a little bit more than just the usual product, but I'm not going to go into the details there. If you're the sigma product, though, you are definitely going to be proximal if every factor is proximal. Since every proximal space is turned out to be collection-wise normal, I can now prove to you this result here at the bottom. Sigma product of metrizable spaces. Metrizable spaces also turn out to be proximal. So a sigma product of metrizable spaces is a sigma product of proximal spaces, which is proximal, which is collection-wise normal. QED, I'm done. That was a really nice, slick proof for what turns out to be a really hard theorem if you don't have all this machinery in the background. So this has been really fun to work with, this property. So what did I do? Well, first of all, Peter Nikos again, he observed that if you are a so-called coursing compact space, basically you embed in a sigma product of real lines, which is a sigma product of metrizable spaces, which is sigma product of proximal, which is proximal. Okay, that was his proof. What about the other way around? What if you're a compact proximal space? Do you have to have all this structure of a coarse and compact space? Me and Dr. Grunhag said, yeah, that actually is the case. You can go the other way around, if and only if. So that's not limited information, but it's a nice application of this game. Another result that I have, I was of course considering the limited information strategy stuff. So I thought, okay, if I have not a winning strategy, but just a Markov strategy or a tactical strategy for the entire space, can I pass that down to the closed subspace? Sure, you can. It's no problem. What about a sigma product, though? Reading Bell's proof, you see that she keeps track of every single move the opponent played for the entire game. You can't forget anything. So then her proof that a sigma product of spaces, you can just construct a new winning strategy from all the winning strategies for each factor. That doesn't work if you aren't keeping track of everything that happens during the game. But if you're only talking about a countable product, which is an example of a sigma product, but a little bit less stuff to worry about, then yeah, you can take the winning K Markov strategy, not K tactical, you gotta use the round number still. For each factor, you can pass those along to get a K Markov strategy for the entire countable product. So I have a few different lemmas along this line of things that Bell proved that I said, oh hey, and here's the same or the similar thing that works for limited information. In my dissertation, I didn't get a nice application of that, but since then I have a paper in preparation where I have this neat result I just recently presented in the set theoretic topology seminar. A compact space is strong Everline compact. It embeds an even stronger type of product, if and only if there's a tactical strategy for this game. So it's kind of analogous to the, oops, where did I go? I went backwards. It's the analogous result here. Coarse compact, if and only if winning strategy. Strong Everline compact, if and only if tactical strategy. And if there's any justice in the world, it will also be Everline compact, if and only if Markov strategy. I don't got that yet. So, that's one of the things I'm looking at. Cool. And that covers that game. So, move on to game number 3. Game number 3, back to one of Dr. Grunhag's games. I'm going to call these things locally finite games. There's two versions, players K and P, which I've drawn here, players K and L, which is pretty similar. I'll talk about that. Here's how it goes. K stands for compact. We're thinking in terms of the XY plane or some nice Euclidean space in general. Compact means closed and bounded. All right, so we're going to take, K's going to pick a compact set. That's going to be kind of forbidden for the rest of the game. The point picker has to stay outside of it. K will pick a new compact set. P has to stay outside of all of the forbidden sets. So on, so forth. The goal of this game for player K is to force these points to disperse, to prevent them from being locally finite in the space. If she can do that, she wins. Otherwise, the point picker P wins. Now, what if you replace P with L? What do I mean? Well, what I mean is instead of the circle representing a point, I mean it represents another compact set. But the game still proceeds the same way. The compact sets have to stay outside the union of K's compact sets for the rest of the game. And the goal is to get them to be dispersed in a nice way for player K. Okay, Dr. Grunhag used these games to characterize metacompactness and sigma metacompactness for locally finite, locally compact spaces. And he used limited information to do that. A tactic strategy characterizes metacompactness. A Markov strategy characterizes sigma metacompactness. And this is probably one of the first things I looked at, because I just saw that and thought, huh, okay. So if I have the latest move of the opponent, I get metacompact. If I have the latest move of the opponent and the round number, I get sigma metacompact. I wonder if that works. So if I don't know anything, the space better be compact if I'm going to win. What if I'm just on the round number? Maybe I need sigma compact? It was a silly, naive thing to think, but it's true. So that's what one of the things I did. For locally compact spaces, if you have a predetermined strategy, you're only using the round number, that's going to characterize sigma compactness. Also hemi compactness and a bunch of other things as well that are all equivalent, known to be equivalent to locally compact spaces. But for locally compact or even compactly generated spaces, having a predetermined winning strategy for this compact point thing, you can use that to get a winning strategy for a compact space. All points are compact, not all compacts are points. So the other direction is the obvious one. So I wondered, maybe there's no difference. If we're not going to even pay attention, give the other player the respect of paying attention to their rules, their moves, maybe there's no difference between these two games. Well, if you remove enough structure, you have to go to non-compactly generated spaces, specifically a subspace in the stone check compactification of discrete omega. You do get a counterexample. You can construct this free ultrafilter, which basically spaces out things enough so that the points would still have to be dispersed, but things are spaced out enough that the compact sets can stay with cluster within the space and cause the K not to win the game. Only if K is not paying attention to the opponent, though. Okay. Now I mentioned, this looks familiar. So I'm talking about this compact point thing, right? Compact point, compact point. It's kind of like the inverse of what I talked about at the beginning, right? Open set, pick a point inside. Open set, pick a point inside. It's the opposite, and that's with good reason, because if you take the one-point compactification, toss in a point of infinity out here, then it's the exact same game. Open sets of infinity are everything not in some compact set for locally compact spaces. So that's going to give us an equivalence between those two games, except you can't actually, the point taker cannot take the infinity point if it doesn't actually exist. And that's the case for the KP game normally. So even though, if you throw in the infinity point, I have this result that says a K+1 tactic and mark can be improved to only use the most recent move of the opponent. It's not obvious that that's going to work for the locally finite game unless you allow them to play this non-existent infinity thing. Do something weird like that. And that's annoying because we have this characterization of metacompactness and sigma metacompactness characterized by the existence of a winning K tactic or one tactic or one Markov strategy. I love it to exist for K+1. As I said, the technical difference, that lack of this extra point, but it makes it very difficult to show that that's the case, if it is the case. However, Dr. Gruenhagen gave me this example. Maybe it was going to be a counterexample. Turns out no. For this space, there's definitely not a Markov strategy because it's not sigma metacompact, but turns out there's not even a K Markov strategy, even though no matter how much information you have, if it's not perfect information, basically, you're not going to win the game. P is going to find you out and find a way to beat you. So that's one of the other things I worked on for that game. Last but not least, I'm going to change pace a little bit. This is an unrelated game to the previous three. It's called Minger's Game because it's named for a property of Menger. Let's see, how does it go? There's two players, C and F. C picks an open cover. F takes a subset of the space, which is finitely coverable by the open cover above. Now, I didn't have time to draw infinitely many circles, but the idea is that each of these things, this purple guy, should be covered by finitely many of the circles. The blue guy should be covered by finitely many of those blue circles, so on and so forth. Now, F can cover the entire space, basically, with these finitely coverable things. By the end of the game, she wins. Otherwise, C wins. It's called the Minger Game because it characterizes the Menger property. I believe Horevich was the one that proved originally that if C does not have a winning strategy for this game, space is Menger, and vice versa. So, it was originally suspected that these Menger subspaces were just sigma compact spaces, the countable union of compact spaces. But it was shown by Topological and Skippers that there's a slight bit more structure there. If you're a metrizable space, sigma compact, X is sigma compact if and only if F has a winning strategy, which is a subtle difference. It's possible to have these games where neither player has a winning strategy. Every time you play the game, somebody has to win, but it might mean that nobody has a guaranteed way to win the game. But if you're sigma compact, that characterizes player F definitely having a way to win no matter what the opponent does. Okay, so one of my results was to kind of take this idea right here, metrizable, characterizing sigma compactness with this game. Well, what if we're just regular? Well, you can still do the same tricks that specifically Skippers did. Skippers used this perfect information strategy in the properties of a metrizable space to get sigma compactness. But if we're just regular, I can use a Markov strategy and exploit that to get sigma compactness. If we're second countable, there's a countable base for the space, then you can take any perfect information link strategy and improve it to only use the most recent move of the opponent and the current round number. And because, in every case here, we're talking about a Lindelof space. Lindelof metrizable spaces, that's the same thing as Lindelof regular and second countable. So, put these together and you get the existing result. But it kind of gives you this nice breakdown using limited information of what's really at play. I'm going to prove those for you. All right. First things first. Sigma compact if and only if you got a Markov strategy. Let's assume the space is regular because we got it. All right. If X is a countable union of compact sets, then player F can choose the nth compact set during each round. Compact by definition means for any open cover, you can finally cover it. So, even ignoring what cover was actually played, player F is just going to pick the compact set Kn. By definition, the union up to the entire space. Therefore, that wins, and it doesn't use anything more than the round number. So it's predetermined. It's Markov. The other way is a little trickier, but if X is not sigma compact, what can we do? Well, let's take any Markov strategy. We should be able to break it. All right? We're going to define these RNs right here. Rn is going to be the intersection of what the Markov strategy says to do for every open cover. We just intersect it all down. Now, for any open cover, by definition, this is finally coverable by U. So for any open cover, the intersection of all these has to be finally coverable by any open cover. So this is what we call a relatively compact subspace. And since we're regular, that turns out to mean that the closure has to be compact. All right, we're not sigma compact. We are not the union of counting many compact spaces. So if we union all these Rn closures up, we're definitely not covering the space. Okay, so let's pick a point X that wasn't covered by any of the Rns. That's what we're going to use to get our counterattack that breaks the Markov strategy here. What we'll do is, okay, X was not covered by any of these guys during any round N. So for each N, I can find the open cover that screwed it up. I can find the open cover that did not cover X. And I'm just going to pick those open covers that make sigma never cover X. At the end of the game, X was never covered. That is a winning strategy, and it only uses Markov information. So, there we go. Excuse me. We broke the winning strategy so that it could not win. And notice that the only properties that we used here, that was a Markov strategy. So for any Markov, I can break it. Therefore, a winning Markov can exist. Cool. All right, the other half. If we are second countable, that means we have a countable base. So what a countable base means that for any open set, there's one of these guys inside of it containing each point. Okay, so let's see here. We can assume without loss of generality that the players are only going to use these guys. I'm not going to go into those details, but it's not too hard to figure out if you play with it a little while. First things first, if you have a winning Markov strategy that uses limited information, well, it doesn't hurt you to use perfect information either. So then we got one direction of the if and only if, no problem. What if you have a winning strategy that uses perfect information? How can you whittle that down to only use the round number in the most recent move of your opponent? We're going to exploit the fact that we're only playing with these countably many open sets. So, we have these open cover and basic open sets. By exploiting the countability of this base, we can say that we've already defined these open covers. We'll take this new open cover that the enemy has given us. There's only countably many possibilities for us to spit out of this guy, basically. Because there's only countably many ways to finally cover something from a countable set. So, for all these countably many possibilities, I'm going to pick a representative that will cover. We'll cover this play using that representative instead. Then what I do is, if I'm going to construct a winning strategy that only takes a look at the most recent move and the round number, I'm going to go through all these. Basically, I have a whole tree of different possibilities, all these different open covers I've defined. But there's only countably many ways of going through this tree by the end of the game. So every round, I assume I'm at one of these nodes, and I take care of that possibility. And then I stick the open set at the end of it, the open cover at the end of it. So by the end of the game, I've taken every single possibility of going through these guys, and that's going to basically say that maybe I didn't play exactly the same thing I would have played with perfect information, but I played something even better that covered it. And that's going to make sure that I cover the entire space. Even though I didn't have winning information, I could fake it well enough. All right, now I'll take care of that. I'll talk about this game a little bit more because there's another angle you can go at this game, and the applications here are not with topology necessarily, but with set theory. These games often have set theoretic consequences that are similar to it. S kappa, and sometimes I'll write S kappa omega omega. It's a statement, it's an axiom of set theory due to Menger skippers, and it says that there exist these things called almost compatible functions for every countable subset of kappa. Almost compatible means that they only differ on finding many things. All right, now we have, and they're injective as well. All right, so it turns out that in the normal rules of set theory, ZFC, it's true that you can find these almost compatible functions for the first uncountable cardinal. It's true that it's impossible to find these for anything larger than the cardinality of the real numbers. However, if you're in between those two, you can't use the normal rules of ZFC to determine whether that's true or false. It's independent. So one thing you can do is say, well, what if we assume that it's true? What if we assume it's false? Well, I'm going to assume that it's true. What can I determine from that? So if S kappa holds, skippers show that there is a two-tactic strategy for this set theoretic game where you have one player picking a countable subset of kappa, another player picking a finite subset. The finite pickers try to overtake the countable picker, basically. Okay, well, let's say kappa to the dagger is the one-point Lindeloffification of a discrete cardinal kappa. Then we're going to have this whole slew of these different topological and set theoretic games. Right here we have another way of writing the Minger Game. Here we have these other games involving first player picks a countable subset of kappa, second player picks a finite subset of kappa. The goal in these games is for the finite picker to overtake the countable picker. The goal in this game is for the finite picker to cover everything in kappa, but the finite picker can also pick the open set containing the infinity point, which takes care of all but counting much of it anyway. So, turns out, all these guys, if you assume that S kappa is true, or as I said, this is the same thing as S kappa, then all of these have to have two Markov strategies or two tactical strategies. What would be very interesting, one of the questions I'm interested in, is, well, what if you have these strategies? Can you use those strategies to construct the almost compatible functions? I don't know yet, but I'm not really seeing a way to win this game unless those things exist anyway. So maybe that's true. Haven't proven that yet. Yes, sir.
I'm curious about the superscripts you have there. I don't know if you explained them.
I did not.
In the middle, fill, sub
right.
CF.
So if it's fill, what I mean is C is for countable, F is for finite, and in all these filling games, let me draw something. Do we have an eraser? Do we have an eraser? There you go. So we're playing in kappa. I don't have time to draw infinitely many points, but let's say there's kappa many on the board there. So the first player is going to pick countably many of these. Okay. The second player is going to pick finitely many of those. Let's do opposites for those. Okay. But there's different rules depending on these superscripts for these different games. The one skippers considered was the finite picker has to cover the union of all the sets played by the countable picker. So not just the first one, like in this one, but the union of all of them. But there's another rule that the countable picker has to always be growing each round. Has to strictly increase each round. In these games, because it's more subset we're equal to, the countable picker can stay still. Just pick the same one. That's why we have to introduce the round number so that we don't get stuck in this loop, basically, of seeing the same thing over and over again. So we keep playing the same thing over and over again. We have to have the round number to see us and push us onward. This guy up here says, I don't care what sets the countable picker picks. They don't have to be supersets or anything, but to make it easier on F, we only have to cover the intersection of all those. And as you can see, that actually turns out to be equivalent to the Minger Game on that topological space. So thanks for asking that. I should have clarified that. Cool. Okay. So in addition to that result right there, for most of the games of that chart, I've only been talking about these two Markov strategies, these two tactic strategies. Well, for the Minger Game at least, and for a lot of these other games as well, if you have a 7 Markov strategy, you're using more information, you're using more memory than you really need to. You can just keep track of the latest 2 because all you really have to do is The topological property, because any existence of a winning strategy in a topological game is, by definition, a topological property. But this seems to depend on the set theoretic axioms at play, as you might expect from the previous slide. If you have that S of the cardinality of the real numbers is true, then you can win this Minger game with a 2 markup strategy. R omega is the usual real line, the usual real numbers, except open sets you're allowed to shoot counting many holes, counting many singletons can be tossed away from open sets. If you lose that structure, it makes it hard to win this game, but with the set theoretic structure, you can win it just using 2 moves of the opponent and the round number. So that's another result behind it. But I've talked a whole lot, so I think it's time to ask you guys for your questions. My references are right here. You can go to my website and download those if you're interested. Yeah, what do you guys got?
So are there any questions?
Are there any situations where you might have more than just 2 players playing a game?
I mean, those are certainly studied. Those get really weird really fast, even with finite games, right? Because you have this, I mean, you've played games in real life, right? You know, if you're playing a 3 or a 4 player game, you have this idea of king making, because you have to consider what if both opponents are playing against you, what if they're collaborating, what if they're not collaborating. It gets very messy very quickly. I haven't seen any applications in topology using 3-player or greater player games myself, but yeah, most of these are 2-player games. You don't allow ties. You know, either you're winning or you don't.
Can
Yes.
you go to the previous slide?
Yes.
The one with the literature.
Yes.
Okay, model. So it's related to some problem of the Scottish book, right?
Yes, that's the citation for the Bach-Mazur game. The Bach-Mazur game, I believe, was first written about in the Scottish book, actually.
Okay, so then is updating the Scottish book. He's
Okay.
preparing a new edition. Maybe you should get in contact with him if you have something new.
It's a very recent update.
He's working on it.
Oh.
He's working on it, and he's about to finish almost. Okay.
Was Dr. Bond the guy who talked at the JMM?
Yes.
Okay.
So the Scottish book was just a set of problems. In 81, what Malden published was based on the conference in 79 in Denton, when Ulam and all those guys were there. Not Banach, not Mazur, but
Right.
some were, yeah. So, but Zygmunt, Granas, Ulam, many people were there. So he made comments. He published this version, which is over here. And now, about a year ago, Berghauser asked him to prepare a new updated version. And there were several problems solved quite recently. Or they may have a partial solution before and I have better solutions. So if you guys, can contribute to that, I'm sure Ben will be very good.
Thanks. Yes, sir.
I wanted to see if I understood a statement you said earlier. You said something about sometimes there is no winning strategy.
Yeah.
And of course, that seems unusual because I'm used to sort of regular games that don't take an infinite amount of time to play.
Finite games, it's a fact. You can basically work backwards from the ending states of the game to show that one player or another, basically you just map out all the possible places that you can be in this game and then map out what you need to do to either win or you can determine that there's a way you can't win.
Right.
But I'm trying to see, yeah, right here. So basically, if this is going to happen, where C doesn't have a winning strategy, so it's a Menger space, but F also doesn't have a winning strategy. If we're metrizable, then we're Menger, not sigma compact. Constructing those is hard. You're pretty much going to use the axiom of choice to construct such a space. There's an alternate axiom of set theory called the axiom of determinacy, which says for games of a certain structure, there's always a winning strategy for one player or another. And I'm not as deeply familiar with that axiom.
That's the Mazur game, I believe.
The I don't think so. I think it's
Well, it's, okay,
it's on Omega to the Omega.
it's the Banach-Mazur game on Omega to the Omega.
Yeah, I believe that's correct. So, and it's only for like that cardinality. You can't get bigger than that, I think. So, but maybe maybe the axiom could work for higher kappa or something. But with the axiom of choice, you can for a lot of these topological games, such as the Minger game, you can break it. I think the Bernstein set is an example. I'm eyeing Dr. Grunhang, he's nodding, so I guessed correctly. The Bernstein set you have to construct with the axiom of choice. It would not give a winning strategy to either player. You could break, so you fix your winning strategy.
In the Banach-Mazur game, not the Minger.
The Banach-Mazur game, maybe not the Minger game. But definitely the Banach-Mazur game, that definitely sounds right. So you fix your winning strategy, the other person can break it if they can figure out what it is, and vice versa. But remember, if you actually play the game with two strategies, someone's going to end up winning. It's just that the person who lost didn't choose a good strategy, basically.
So finally, a game where computers will never overtake humans. Or maybe not.
It would take a long time for a computer to finish these games. Anyway. I always describe these games because they're infinitely long. Like, how do you actually play them? The game you're really playing is, I'm going to create this strategy. I'm going to define this, what I would do for round N. I can do that. But I've never finished playing one of these by hand.
So you don't have a win-loss percentage?
No. I'm still working on the first one. We'll see how it goes. Yes.
Yeah, have you considered games of length longer than Omega?
I've read a little bit about them. I haven't considered them yet. I have a paper that's Dr. Grunhang gave me on Omega one-week games. In particular, I know the game was done limited information strategy set with Omega one-week games, and I'm very interested in that. What would that even mean, especially like the limit case? What would that mean? But I have yet to look into those myself.
Other questions? Let me ask my committee members. Stu asked a question. Michelle, do you have any questions?
Actually, Stu asked the same question I was thinking, but you got that first.
Okay.
Fine.
Okay. Chris?
Nope, good.
You're good? Stan, would you have any questions? No? Okay. Then I think we're good. Let me ask everybody except the committee members.